Let's revisit the pattern matching problem in which we have a single long database sequence of length n, and ignore this $sign for now. This is a null termination character that I'll bring up later. But our database sequence is length n, and we have m query sequences, each roughly of length k. Our database doesn't change very often, but our queries may change very frequently. And we want to find all instances of every single word in our query as it appears in our database string. So we looked at suffix arrays, which provided us a pretty good solution to this problem. We basically pre-processed our database, and then we created a data structure that I could do a binary search on any given query to find where it occurs in my database. And I could actually find every single instance of where every query occurs in my database. For each query, this operation was big O of log n, potentially times the length of the string, but generally speaking, it scaled logarithmically with the length of my database. This is pretty good. It's better than a linear scan. But can I somehow do better? Well, it turns out that I can use what's called the Burrows-Wheeler Transform to make this even faster. So the Burrows-Wheeler Transform, or BWT, was actually discovered in order to improve file compression. The reason for this is that this transformation is a reversible transformation, so I can actually reconstruct my original sequence from its Burrows-Wheeler Transform. And the Burrows-Wheeler Transform sticks together similar letters into strong, long repetitive substrings. So we actually won't be talking about data compression, but we'll be able to leverage this seemingly unrelated topic to help us with fast pattern matching. So what exactly is the Burrows-Wheeler Transform? So I take my database sequence with an added null termination string, or a null termination character. Basically, whatever my alphabet is for my database sequence, add one character to the end of it that's not in that alphabet, and that will be my null terminator. So here, that's the $sign. And then what I do is I have to first create all rotations of this sequence with the null terminator. So all of those rotations would be banana, $sign, then rotate it, so I get $sign banana, then rotate it again, so A comes over, a $sign banan, then rotate it again, so n comes to the beginning, a $sign bana, then rotate again, I get Anna, $sign ban, rotate again, I get Nana, $sign ba, rotate again, I get A-N-A-N-A, $sign B. And then if I were to rotate again, I would get the original one. So I first generate all rotations of my original string. That is this matrix here. Then I sort all of these rotations alphabetically. And I will assume that my null terminator character is the smallest alphabetically. So this null terminator, the $sign, doesn't appear in my alphabet, and I'll actually assume that it's less than all the characters in my alphabet. Okay, so let's sort these alphabetically. So the first one alphabetically is the one that starts with my null terminator, which is this one. Okay. Now next would be something that starts with an A. I have a $sign versus an. A $sign versus an versus an. A $sign is the smallest. So a $sign, B, A-N-A-N. Okay. Now I have A-N-A $sign versus A-N-A-N. So A-N-A $sign is smaller. A-N-A $sign, B-A-N. Okay, now I have A-N-A-N-A $sign. That's my last substring. That's my last rotation that starts with an A. So A-N-A and a $B. Okay, so that's all of the A's. Now the next alphabetical order is B. There's only one rotation that starts with a B, so that's the next one. Banana, $. Okay. Next is N. There's two that start with N. NA $ versus NAN. NA $ is smaller. So I get NA $, BANA. And the last one is Nana $BA. So Nana $BA. So that was easy. I just sorted my rotations of my sequence with the Terminator character, and I got this here. So the Burrows-Wheeler transform is just the last column of this matrix. So the Burrows-Wheeler transform, Burrows-Wheeler transform of the string banana $, is just A N N B $A A. So it's pretty easy to construct the Burrows-Wheeler transform. Again, compute all rotations of your string, take the last column, and that is your Burrows-Wheeler transform. In practice, when you're sorting the rotations, you don't actually have to store them entirely in memory. You can just kind of on the fly, because all we care about, we don't care about these middle characters. All we care about is basically the first column and the last column. So you can construct these rotations on the fly given the original database sequence. So in practice, you wouldn't create this n by n matrix because that's way too memory inefficient. But either way, that's the general idea. So this is our Burrows-Wheeler transform.